All right. Let's see. Okay. Hello, everyone. Now, once again, we have a new setup. I know it seemed like my setup has changed every week, and that's because it has changed every week. I'm in yet another house. Hopefully, this is the final destination. I'm in my new house. But sadly, I've not been granted the absolute gift of the notional broadband network. I've not been given the gift of the NBN by the Australian government just yet. So, this might scare a couple people, and scared me, is currently running off a like a USB tether on my mobile my mobile data, which I just wasn't gonna dare to overdo until I actually started doing some testing, and I was like, okay, 4G is actually pretty quick. Maybe I can. And I've done testing, and it seems like from 6 to 8 p.m., which should be like the real worst time, it holds up at like a high quality 1080p stream. So I hope we survive through this. But if things go wrong, it's probably my end, not yours. So don't panic. Anyway, fingers are crossed. But we've dropped 0 frames, and on my second test stream, I also dropped 0 frames over like a couple hours. So thank you very much for the good luck. Yes, and we shouldn't have a problem with running out of data or anything, because I'm on a mobile data plan where the data I don't use rolls over into the next month permanently with no limit, and so I've saved up half a terabyte of mobile data over a couple of years, and now I get to spend it. Now it's all coming together now. In which carrier, I don't want to necessarily I don't necessarily endorse them, and this is not a sponsored lecture. But I use Aldi Mobile because I personally like the Telstra network, and they have at least a portion of the Telstra network in particular. Everyone seems to be on the Optus network. Optus loves to sell off bits of their network. Telstra only has used to be 3, now it's like 5 or 6 carriers or something. Anyway, Casual Lecturing must pay well to move into new houses every week. I mean, even if it was, who really wants to move houses every week? It's not been fun. Speaking of, moving houses and being very busy and the likes, I had took a chance a couple days ago to catch up on, I think I've caught up on all the emails to the course account, and we did a big run through the course forum, and I think anything that's not more than anything that's more than, say, 24 hours old or something like that has been responded to. We've tried to resolve whatever we can, and I think a couple things we just needed some more information. But if you think that, if you believe that an email of yours has gone unanswered, or you have something old on the course forum that may have been missed, just let us know. Let us know however you like. You can send another email you can full caps your subject line if you think we're missing emails from you or something like that. But I think we're mostly caught up at this point. So, and apologies for, having taken a little bit to catch up. Okay, so let me see the chat here. So hello to Mitchell, Dong, Simon, Cece, Andrew, Josh, Miguel, and Kai. So mobile data is usually better than NVN, HFC. Optus, sponsored? No, not sponsored. Voter Gang, license number, Vodafone, okay, yep, and other data carriers. Okay, cool. And yes, everyone is famous now. All right, great. So, this week, we are looking at polymorphism. And this is a particularly interesting topic for this course because Rust I'm going to word myself carefully here. Rust is not a like die-hard, exclusively object-oriented language. Languages that I might throw into that category are, vaguely things like Java or the Java family of languages, or something like Python, where they're very committed to the idea of object-oriented programming. Even if Java or Python really has like, say, functional capabilities, the vast majority of like data and behavior that you're dealing with are in terms of objects, where there's this sort of one sort of all-seeing object at the very top, and everything, there's a lot of inheritance sort of all the way down classically in these kinds of languages. Now, Rust, again, is not quite so object-oriented to that point. C++ is pretty object-oriented as well, but you can sort of, you can certainly opt out of it and do things particularly differently. What I would phrase Rust as having is object-oriented capabilities. So some of the things that you'll find in object-oriented languages, Rust either has like a very sort of an equivalent offering, and then for some features are missing. For example, inheritance isn't really present in Rust. There is inheritance sort of over lifetimes, but that's not really generally a thing that you tend to think about. You just think of lifetimes getting shortened, but technically it's a system to do with inheritance. But there's specifically no inheritance over types. There's no, say, golden retriever extends dog, extends animal, extends object. I don't know, maybe there's something between animal and object, but I don't know. So you don't get this sort of chain of inheritance or anything like that in Rust. But some of the patterns that you'll sort of spot in object-oriented programs can at least be emulated as well in Rust. We're going to look at that in terms of the classic animals example, and look at how we can get some sort of object-oriented capabilities, and also like sort of things that look slightly like inheritance, but not quite the same thing. Okay, and sure, family, species, subspecies. There we go. We've got the biologists coming in, so perfect. But yes, importantly, this pattern is generally not quite so is not expressed in Rust so much, let's say. Okay, so to outline, in fact, speaking of outline, it might make sense to just pull up our outline here, and yep, checking stream, all looks healthy. Topic notes. So this is the polymorphism week, and we're going to talk about generic, that S has snuck its way in there, generic type parameters, which if you're a very diehard theoretical programmer, you might know as parametric polymorphism, more specifically bounded parametric polymorphism. If you don't know what those words are, then that's not really a problem, because we're not a PL theory course in the same way. We have theory aspects in our own way, but not specifically PL theory. We're going to talk a little bit about monomorphization, which is how generic type parameters are implemented. These words are all going to sound scary, but at the end of the day, it's actually, I think they're relatively simple ideas that you just have to play around with and you'll get used to. We'll then talk about traits, which allow in particular ad hoc polymorphism, which is sort of distinct from parametric polymorphism in this case. And then we're going to look at static versus dynamic dispatch of those traits, where usually you will opt for static dispatch, just when you're generally using traits. But occasionally we opt into this dynamic dispatch with something called the DYN keyword, which is DYN out of dynamic here. That's like all the stuff that we're going to play around with this week. We'll see how far we get today. And then that'll sort of inform our lecture on Wednesday. Watched a video about it recently. Very nice. And we have a cat coming out of a box. Shrey says it's definitely not. Well, I don't know what's definitely not. Cool. Anyway, so that's what we're looking at. And we're gonna start off. We're gonna be talking a lot by example as well. People seem to like things being shown by example as opposed to just like things on a slide. So we'll start off with that. And stream check, everything looks good. Good. So type parameters. We're starting off with the generic type parameters that we've mentioned over here. And you can see I've written some kind of painful looking code right here. So I'm going to give you a sec to just read through this, and then I'll run through it again, and then we'll have a chat. So we've got 3 functions, and they all basically do the same thing. In fact, if you look at this body here, this is going to be the exact same in all 3 functions here. It's just trying to find the smallest of 2 values, right? But let's say I want this function to work, whether I give it integers, whether I give it floats, whether I give it characters, or potentially some other types you might want to throw in there that could be compared to see which one is greater or smaller. Oh, it's definitely not fun to move houses. I see. Okay. Yeah, it's not that fun, is it? I'm not sure. I also turned like up the stream delay. I'm not sure how big of a delay that's actually turned into, because I wanted to. If there's a hitch in the stream, it's more likely that things will survive. It's on low latency mode. So anyway, I'm not sure how far behind the chat is, but you might be a little more behind than you're used to. If it's particularly bad, I might try and drop back down to ultra low latency mode, but I'd have to stop the stream and start to do it again. So we'd have to do that for Wednesday. Anyway, so the chat might be quite far behind. I also just realized I missed a message that said traits is equal to interfaces in Java. Yes, they're very much an analog of one another. I believe traits in Rust open up more possibilities than interfaces in Java, but traits offer at least what Java interfaces offer, plus potentially some more. 10 seconds or so. Okay, cool. That's not too bad then. Traits D. Thank you. Okay, anyway. So, I want this function to work across all these different kinds of data types. And so far this does. Right, I write one function for i32, one function for f32, and one function for char. And if I go cargo run, you'll see the smallest i32 of 42 and 100 is 42. Excuse me. The smallest f32 of 3.14 and 99.9 is 3.14. The smallest character of A and Z is A. In fact, I also just realized the smaller one always comes first, so I'll prove to you that my code is not, oops, 1,000. I'll prove to you that it's actually doing the right thing. We still get 42 if I change the order up. So it's really working today. Shrey's on fire today. All right, cool. But this kind of sucks. If you are a diehard Go programmer, as of maybe more than a year ago or so, 1 or 2 years ago, you may disagree with me and may say this is actually very good code. I'm personally not a fan, and I'm happy to leave it to you to sort of make your own judgment on this, but I'm going to show you tooling that we have to not have to do this. So I mentioned Go, Google's Go language in particular, because prior to 2 years ago, this is about as if you wanted to write code to do something like this in Go, this is what you end up having to write, essentially. There are tricks around it. There's tricks to do with like boxing and performing some horrible curses. And also a very common thing in Go is to write code like macros in Rust we haven't really talked about yet. Essentially write code to generate Go code. So you go write a program that spits out this function, but for like whichever type that you want here. And yeah, this is a decision by some languages. In fact, in C as well, we have the same problem in C. And often C programmers will use hash defined macros to work around this kind of limitation. If you're not a fan of like repeating lots of code many, many times, you may like the idea of just writing this function once and having it applicable to whatever type you use. Now, of course, there may be downsides that come along with that. And that's almost certainly going to be the case, however you perform it in whatever language. But it's useful to, I think it's useful regardless to have the ability to do it. In our case, it certainly adds to the language's complexity in terms of like the feature set of the language, but it may also reduce the language's complexity in terms of, you know, not having to worry about generating 50 functions if you need a function to work on 50 different types. So it may increase the complexity of understanding the language, but may decrease the complexity in writing code in that language. Again, it's up to you to sort of form your own opinions on this over time. My typing has been bad, as Zach can attest to, but yeah, basically saying that traits can do a lot more than interfaces. There's a talk called Traits Are Not Your Grandfather's Interfaces. We'll link on the forum. Awesome. Generics are amazing. Anyone who disagrees is wrong in my opinion, says Miguel. Stop trying to take selfies while typing Shrey, and Shrey's leaving. And implement generics with custom sed commands in the middle of my build chain. Right, yes. So that would be the 2020 Go programmer's approach, I suppose. But we're going to look at how we can sort of do this in Rust. So the first thing, like we've written 3 of these functions, we need to figure out what they have in common, right? Like what they have in common and where their differences lie. So one thing we've noticed is that the body of all these functions are the same. They do the same thing regardless of what type it is. Now this less than operator might act differently depending on what type it is, potentially. For example, comparing chars might not be as simple as comparing ints, and comparing floats has some baggage associated with that as well. They're conceptually doing the same thing. They're checking if one thing is less than another, but the implementations might be different. It's something to keep in mind. But the code here we've written is all the exact same. So ideally, what would we like? We'd like a function that's just like smallest, not smallest i32, not smallest f32, whatever, just smallest for any type. We take an x, which is, well, whichever thing the user wants. We take a y, which is anything the user wants, and we return back the smaller thing here. And what's this code going to do? Well, it should, in theory, do this. If x is less than y, then give back x, otherwise y. So that's what we're sort of looking for. Now, let's say this question mark represents some type, right? And let's say the question mark can just be like any type that we want here. There is, you know, in this definition that I've written here of smallest, there's one additional constraint across these question marks here that I haven't really expressed that is important in terms of finding the smallest. Can anyone think of something important across these 3 question marks in their totality that's important for the smallest function that I haven't necessarily like mentioned just yet? There's a couple things you could answer here, and I'm looking for, out of the few things I can think of that you might answer, I'm looking for a simple one, but I'll see what the chat says in about 10 seconds or so. So you want the type to be comparable, i.e. you can do the less than operation. Absolutely, yes. And the chat is now coming through. Yes, they must be the same type, they're the same. The question marks have to be the same. Yes, you're all on the money. So the one thing that's important here is that the question mark, if it represents any kind of type here, there's an important constraint that all 3 of these question marks must be the same. We can't have i32 compared to a char which spits out a float, right? Like, this is just nonsensical and not something that we want. Okay, so we know sort of what we want here. Now, how do we actually get there in terms of Rust? So these sort of question marks that I've put here, this is just not Rust syntax at all. Question mark is that operator to do with options and results and stuff that we've seen earlier on in the course. I think we'll also use it again later today. So what's the actual syntax for this? Well, I sort of need to make this smallest function generic over some type. Now, what should that type be? Well, it should really be any type that the user wants. We might want to sort of constrain things later on, but for now we'll just say any type. And the way that we introduce this generic type parameter on our function here is right after the function's name and before the argument list, before these parentheses, we throw in crocodile brackets, angle brackets, whatever you want to call them. I feel like as an Australian university, we have to call them crocodile brackets. So we introduce these crocodile brackets here, and then in these brackets, we can sort of name a new type that we're making up. Now, a really common, You know how very commonly, if you don't have a name for a variable, you'll use like X or Y or foo or bar or baz. In terms of type parameters, people tend to use T as like their first, just like, I'm just naming a random type. Note that this could be anything. I could call it foo, I could call it bar, I could call it baz. And you could call it, you know, who's in the chat now? We could call it Simon, right? And this is all fine. Rust has no problem with this. But when you don't have a good name for something, people generally start with T, and then often they go on to U, V, you know, and sort of iterate that way. But we're just going to introduce a new generic type parameter called T, and this, according to Rust, is just going to represent any type, right, that the user, the caller of the function can specify. And we're going to say, well, what type does X, Y, and the return value have? Well, we'll say X will be a T, Y will be a T, and the return value will be a T. Right, so now smallest, it doesn't know the types of these parameters in this return value here, but it knows that there'll be some type T, and T like will be the type of all of them. So notice if I wanted them all to be completely separate types that could just be whatever, I could write, say, T, U, V, and then this would be U, and then this would be V. And now these are all just going to be 3 completely random types that, you know, may not be related to one another. They could all be the same. Like someone could call smallest, right? They could say, I would like to call the smallest function with I32, 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 and that might be fine. But they could also just say I32, F32, and char and provide 3 different types. Notice if we said just T, and this is here as a T, and this here as a T, oops, then they only have one thing to specify. They can't say I32, F32 because there's not 2 things here, there's just one. And as soon as they specify that one type, it implies this constraint on X, Y, and the return value here that they all must be I32 now. So this is us introducing a new generic type parameter. And you'll notice I'm using this turbofish syntax. I think I've mentioned this in a workshop or two. Basically it's saying call the smallest function where the generic type parameter here is, we're subbing out T for I32. You very rarely have to write this syntax here. The most common example of where you'll use it in Rust is with the collect method. Like if you have my thing.iter.map with something.filter, .map again, I don't know. And then eventually you want to collect it back together. Collect needs to know what kind of container you want to collect into. Do you want to collect into a vec, into a linked list, into a hash map? You know, what are you trying to put all these elements into? And you specify that type parameter, say like this. You would say call the collect function with the type parameter of vec I32 potentially. I'm just sort of making up an example here. And that would work because collect, much like smallest, defines a type parameter that it uses there. Most of the time the Rust compiler can just figure it out for you though, in that if I type in like 42 here and 100 there, it'll go, well, you're calling smallest where X here is 42, which is an I32 in this case. That means T is an I32, and now it's resolved the types of everything else. And so a lot of the time you don't need to specify it at all. The Rust compiler will just go, you've used, you know, even if it looked at Y, it would see you've used an I32 for Y. That means Y is of type I32, but Y is also of type T. Therefore, T is I32, and it's figured out how to call this function essentially. Okay, so let's start with that. We've got our smallest function here, and let me catch up on the chat because I saw it flying by a little bit. Oh, okay, we're talking about crocodiles a lot. Crocodile safety, type safety, more crocodile. Can we impose some restrictions on what T could be looking at chunk map? Yes, and in fact, we're going to have to. So if you're a diehard C++ programmer, you might look at this function and go, great, we're done, right? Like this seems perfectly fine to me. The equivalent here in C++ being something called templates. And the idea of C++ is when I call, like let's say I throw in another test case here, oops, debug. I throw in another test case where I say 42, 100. C++ will essentially just throw these values in here. It'll throw in, you know, I32 and I32 42, 100, and it'll see when you call this function, it'll see that, yes, I32s can be compared, right? I32, you can do the less than operation, and therefore this function call works. But this doesn't work in Rust. Again, I mentioned this a little bit before. If you enjoy the idea of PL theory, this is what specifically makes this parametric polymorphism bounded. We're gonna look at what this sort of idea of being bounded means right now. So why doesn't this work? If I try and build our program, maybe I'll get a little bit more room for our error message. Here we go. Binary operation less than cannot be applied to type T, right? So X is of type T, Y is of type T, and the error here is on this less than operation. And it says, help, consider restricting type parameter T. Notice, remember Alex in the chat there saying, can we impose some restrictions on what T could be? Consider restricting T and say that T has the capability to be partially ordered. PartialOrd. Oh, interesting. So what's going on here? When we write this code here, it doesn't care how anyone else might call it, right? The Rust compiler doesn't look at everywhere smallest is used and make sure every time someone's using smallest, the stuff that you're doing inside the function is okay. That's just simply not how Rust works. Instead, this function needs to be okay on its own in isolation, right? Like if we just consider this as its own unit, this must always be okay. But the problem is that it's not always okay. Why not? Well, if I substitute T here for something that can't be ordered, right? Something that just has no inherent ordering, like say, I don't know, like I made my own struct up, like struct foo, and foo just like simply cannot be ordered. There's no real ordering to foo. Or in a case where there's no ordering defined because it might not be entirely obvious. Like for example, if we had T is an option of I32. Now I32s can obviously be ordered, but how would you order options of I32s? You might say, well, I think all the nuns should go at the front, like all the nuns should be less than it, and then all the sums get ordered, like so you might, if you have a list that's like none, sum 1, none, sum -5, you might go, well, I think that should be ordered none, sum -5, sum 1. Someone else might come in and go, no, I'd rather have all the sums first, sum -5, sum 1, and then none, all the nuns sort of go to the end. This is a case where the ordering, right, how should you order an option of I32 might not be entirely clear. And for that reason, option doesn't define an ordering. But I mean, the simpler example is just a struct that you make up that just has no real ordering to it. Like if maybe a struct student, and it has a name, they have a ZID, they have a WAM, always going back to this example here. And the question is, how should you order a student? It's not really obvious just on its own. Should you order them by name, order them by ZID, order them by WAM, and then how would you order them by WAM if you chose to do that? It's just not obvious. You'd have to sort of, you have to give some extra information on how you wanted a student to be ordered in this case. And so, because of this, this smallest function here is not really fit to exist for just literally any type T, right? That's my job here to say that this function is not okay is if I can find just one type T where this function doesn't make sense, then the function is not allowed, right? I have a very easy job. If you wanted to prove that this function is okay, you would need to prove that for literally any type T that anyone could ever have, this function should make sense, right? So how do we make this function work? The compiler gave us a very big hint here, which is restrict the type parameter T. Don't say literally any T ever could possibly be used. Only allow T's that support ordering, right? T's, values of type T, where T defines this less than operation. So where does the less than operation come from? We get to jump ahead a little bit in the slides. We've done becoming generic. We're halfway through this, and get to look at some common standard library traits. In particular, PartialOrd here is the trait that we're looking at. So let me pull that one up. PartialOrd. Slow. Stream is healthy. Okay. PartialOrd. Okay. It's all right, I think. I'm worried that things are slow on the internet, but stream seems happy. And it's a trait for types that form a partial order. If you're a mathematician, you might be getting all excited over the terminology of partial orders and total orders and all that. For us, lesser beings who aren't, so mathematically inclined, it basically means that it defines less than, less equal, greater than, greater equal, right? These operations here. If your type implements PartialOrd, right, then you can use these operations on that type. And if we look at implementers, like there's a ton of things that implement ordering. So if we look at a couple examples, IP address, right? You can order IP addresses. You can order orderings. That's weird. You can order booleans, I guess. That would be false then true, I suppose. You can order characters. You can order floats. You can order integers. You can order strings. More integers, all kinds of stuff that the standard library does by itself. Durations, that's another cool one, like 1 second versus 1 hour. And so, there's all kinds of things that are implemented like this. And you can also implement partial orderings on your own types. If you decided that there was one sort of clear ordering for, say, students, maybe by ZID is the most obvious one, you could definitely implement PartialOrd of students for yourself. Oh, options do implement PartialOrd. All right, well, my example is moot. I guess it does, it must order by none then some. There you go. That's the right answer, apparently. That's a fun one. I wasn't aware of this, but now I am. That's how it goes with this language a lot of the time, because I'm not going to memorize every single traits, every single implementer. I've just run into one where I'm like, wow, that's surprising. Cool. But so this trait is implemented on a whole bunch of stuff, and it essentially means that once you implement it, you can use these operators. So do we want literally any type T then? Well, probably not. We want types T where they implement the PartialOrd trait, which allows us to use this operator. So let me impose that restriction rather. The compiler suggested that we just put it right here, and I'll just show you how that worked, but it's not my preference personally. So we say smallest is generic over a type T, where T implements PartialOrd. If I save the file, you'll see that this no longer errors. Why does it no longer error? Because it knows that T defines PartialOrd, and the requirement on the less than operator is that the type is PartialOrd, so the compiler is all happy. And if we run it, you'll see that we get smallest of 42,100 is 42. So that seems cool. Now this is going to be semantically the exact same, but I'm going to show you how I prefer to write this myself. I prefer to write smallest of T, right, is generic over some type T, and then after the return type, but before the starting brace, you can introduce a new separate block called a where block here. So we have function smallest of T, takes an X, which is a T, a Y, which is a T, and returns a T, where T is PartialOrd, like this. I prefer to write it like this, because when you end up with like a few type parameters, or if your constraints get a little more gnarly, being able to say like where T is PartialOrd, where Y is foo, where Z is some bar trait, and you can like there's all kinds of constraints that you can sort of put in here. So being able to sort of lay them out over a greater space as opposed to pushing all the parameters towards the right is my preference, but these mean the exact same thing as what I wrote above. So I just write, generic over T where T implements PartialOrd. Okay, so this is what I wish C++ did. And yes, if you're in Java, T extends bar is your sort of quite similar idiom here. Derive PartialOrd, yes. C++ friend functions weird and painful. Java generics are decent. Runtime penalty. Meta ordering. Meal and lecture isn't God. I'm assuming it's possible to impose multiple restrictions. Yes, and we've just seen that as well. Oh, sorry, on the same type. Right. So I could say that T is also PartialEq, for example, which means that it can be compared to, like, you can say if T is equal to T or T is not equal to T. I could write that like this, or alternatively, you can use this syntax, which is a plus. So T implements PartialOrd and implements PartialEq, and this syntax can also be used up here as well. So like T is PartialOrd plus PartialEq, but you can see this stuff is already starting to drift across to the right quite a bit. And so I probably either write it like this or potentially like this. Those are both perfectly fine to me. And like, we're not going to mark you down unless things are like seriously egregious. You are free to make up your own preferences. As long as we can reasonably read your code, then we're not going to care about small things like this on stuff like the assignment. Okay, as long as you're on the ideas, right? The idea is the most important part. Okay. So that kind of makes the signature look like the Rust doc. Yeah. And yeah, I'm a fan of this. So let's see if this fixes our example above here. So we'll try that out. Cargo run, and there you go. It works on two things, two I32s, two floats, two chars. And if we defined some struct student, right? Struct student, ZID is a U32, name is a string, and wham is an option of F64, I was saying. Hash derive PartialOrd, PartialEq PartialOrd, sure. Now, you'll find that if I do let, all right, who have we got? Let dwang equal student. ZID is 1, 2, 3, 4, 5, 6, 7. Name is dwang, and wham is 100. And then who else have we got? Let shupang equals student, and I'm going to do a slightly different ZID. Let's do 7654321. Name. There we go. And wham is 100. Everyone gets 100 whams in the lecture examples naturally. Now, will this smallest function work with students? Even though the smallest function never intended, to be done on a student, will it work? Dwang and shupang like this. It's not happy because it doesn't know how to print out the student in the debug print. You know how when you call it, it also prints out the code, like the text that was there. It doesn't know how to format a student. So I also have to bring in debug as well. But if we do this, you'll see that the smallest is dwang because the ZID is smaller. If we made the ZIDs the same, it would probably order by name. I would imagine, like it would move on to the next thing. And that would still be dwang, I suppose. But if this was, say, 1 ZID less, then we would get shupang. So there you go. The smallest student, yes. Cool. So this function never intended to be called on students, but it just magically works. Because what smallest really cares about is that you can order the parameters that you bring in. Awesome. That's pretty cool. Okay, so there is something that we can make a little more generic. Like this function here is pretty nice, but we could even go like one sort of step up here in terms of what we could. I like the terminology. This is a terminology that is completely made up, maybe by me or maybe by someone else. I like the genericize terminology to make something increasingly generic. That's completely made up, but I like saying silly stuff like that. There's something further that we could genericize about our smallest function here. Can anyone think about what sort of, what's a potentially unnecessary restriction on the smallest function right now that we could make more generic and sort of give you more possibilities while still working with, the same, with the context it already does, let's say. Does partial ordering imply partial equality? If something is equal, it is not less than. If something is, let's see, we're gonna have to pull up the trait docs here. So the first thing you'll note is that partial ordering on a type requires that that type also defines partial equality. So that in particular is whether they are, checking whether two things are equal or whether they're not equal. And it says, you might be able to prove based on the, what they say the requirements on these types are, you might be able to prove that that's the case, but I'm not going to go too deep into it live in the lecture. But if you are interested or you can't, you give it a try and you're not really sure, definitely ask on the forum and we'll see if I can figure anything out. Sort of related, but I'm assuming an ordering on options would break down if the option doesn't contain an orderable type. That's a really awesome point. So the question is, I mentioned, oh my god, options do define orderings, but, how can we order an option of something that doesn't define an ordering? And if we look at this implementation down here, we might be able to read it a little better now that we know a little bit more. Where did it go? Option. I thought it was right around here. I gotta squint my eyes. Option. Where did it go? Fine, I'll control F. Like a absolute noob. Taking here. There we go. Have a look at this. Implement for any type T PartialOrd of option of T for option of T. So this is saying implement a partial ordering where you can order two options of T's together, but only where T can be partially ordered with other T's. Wow. So the reason T is sort of appearing twice here is because PartialOrd allows the possibility of ordering things of different types, which is actually one thing we could make more generic in this function here that I actually wasn't thinking about when I was mentioning making it more generic earlier. But in particular, it's basically saying only implement PartialOrd on option T's where the T itself can be ordered, which is pretty cool. Which makes total sense to me, at least. So yeah, it's baked into how they implement the type there. And I'm assuming we might even be able to look at this. Oh, because it's done by the derive. I was hoping that we could look at the implementation itself, but it's just derived, sadly. So okay, we had that. It requires less than or equal, greater or equal, and greater than, not just less than. Yeah. Cool. So, okay, what I was looking for here is we've written a function that gets the smallest value of two values, right? The smallest value of two values. But we could potentially make this find the smallest value of any number of values, right? Of 3 values, of 4, of 5, of 6, right? Now, there is some considerations to make here, which is if we say any amount of values, there could be something that could go wrong. Can anyone think if we sort of extend this to any amount of values, what's a problem that might arise in the way we deal with this problem? I get to sit here quietly now because of the greater delay and patiently wait. What's a problem that could arise? Separate arguments versus using a collection. Yeah, okay, so that's an interesting point. Is that if we might want to sort of make this like an n-ary function where it takes any amount of arguments as opposed to, or sometimes that's called like a variadic function versus taking in some kind of collection. If you've used variadic arguments before, which often looks something like this in some languages, where it's like you may have any amount of t's passed to this function. Rust doesn't have that, at least yet. There are some talks about it. The general consensus is there's a bit more pain in variadic arguments than they bring to the table. But there's so Rust doesn't have variadic arguments. So if we're using, if we're talking about any amount of values, we're probably going to need to be thinking in terms of collections, which is absolutely true. And that's, I think, the variable number of function parameters there as well. Lifetimes of the return value probably needs to get annotated. Maybe, potentially. What I'm thinking of is there any amount, let's say we're taking some sort of, some collection or whatever of arguments. Is there any amount of arguments that might cause us a problem? When there was 2, we had no problems at all. Very easy to write. If there's 3, I think we could make that work. 4, 5, yeah, seems reasonable. Are there any amounts of elements? 0, right? What's the smallest of a 0 element collection, right? And so now I would say like a 0 element collection doesn't really have a smallest value. And in fact, if you were to say, I'll just change this to x's, and let's say we take in a vec of t. We'll look at changing that later. If there is the x's is empty, right? Let's say if x's here dot is empty, like what are you gonna do here? You could panic maybe. Oops, panic. But panicking is like you shouldn't like opt for that where possible, because it's very difficult to recover from a panic, and someone might want to call your smallest function, and if it goes wrong, do something else, right? So this isn't really that good. Return default, right? So maybe there's some default value for t where like if we don't find a smallest, we'll return the default value. But the question is, like, what can I do on a t? If I ask Rust Analyzer, what can I do? Oh no, the stream. Come back. The message could not be sent. Oh. We're coming back. Okay. I think the bit rates come way back up. And it's just gone way back down. And it's going way back up. Don't you dare go way back down. Don't do it. Okay. I think it's good now. Okay. I'm going to do a ping test. I'm going to say type pong in the chat right now. Like type pong as fast as you can. I'm saying ping, and I'm going to see how long it takes for the pong to get back from the chat. I'm going to say it was about 32 or 33 seconds passed reasonably. And pong. Okay, about 15 seconds delay. All right, let's keep going. I think we're okay. Cool. It's funny seeing the whole chat go pong. All right, some people maybe have more like a 25 second delay or something like that, but we're gonna power through as CC says. So like if we wanted to return some default value, right? Well, where are we gonna get that default value from? Okay, it's fine. All we know about t is that it can be ordered, right? Is that it can be partially ordered, right? You can do equal, not equal, greater than equal, greater than, less than equal, that sort of thing. But we can't just say, we can't just like give a default value back. So in fact, if we wanted to do something like this, there is a trait that allows us to do something like this, which is the default trait. So the default trait, when it loads, simply defines one function default, which returns like one of the type that's implementing it. So if you define default on say I32 or something, you might say the default value is just something like 0. And so you'd implement default and say spit the value at 0. So we'd actually have to say, to call the smallest function, t must not only support partial ordering, but you must also be able to get a default value. Now this might work. This would work. But now there's a case where what if someone wants to use this on a vec of t's where t doesn't have an obvious default value, but they know that the vec will never be empty, so that shouldn't be a problem. They cannot use this function anymore because you have a requirement that t always implements a default. Right? And, you know, it sort of imposes a restriction. Now we've sort of like walked a little bit backwards in terms of if someone just wanted to do the case with 2 items, now they also need to make sure that the thing provides a default. Like say in the case of a student, right? Like this, our student example here no longer works because student default is not satisfied, right? Default is not implemented for student. And so we'd need to say, well, what's like the default student, right? Impl default for student. And the question is like, is there even like a default student? Does that even make sense? And so the sad thing is maybe we just like can't do this smallest function on students anymore, because there's like, if I just said z_id 0 and like name empty string, that's not actually like a student. Now, anytime anyone uses a student, they need to worry, is it an actual student or is it like the student with 0 empty string none, right? And we're back straight back to like null pointers and stuff and the stuff that comes along with that. So that's almost like a little dangerous. Default student is 5 for 5 for 5 for 5. Yeah, actually, surprisingly, CSE does have a student Z 5 for 5 for 5 for 5. So they have to think about that, which is just great as well. Anyway, so that's potentially problematic. The more sort of rustic potentially student, oh Dong just got Pong, is potentially to turn this this return type into an option, right? And if the vec is empty, then say none. Otherwise, we can find the smallest of the sequence. And you know, we've sort of stepped a little bit backwards in terms of now people have to think about whether their sequence is empty or not. Or there's one other maybe particularly clever way that we could sort of write this function such that it'll always work and we don't sort of trade anything off, which is return a t and then take the first t in as a parameter, right? This is just the first element of the list, and then give us the rest, right? Give us the rest of them. And so if this is empty, that's fine. Like we always have at least the first thing. And then if this is not empty, we go through the rest and see if any others are smaller. And so that's potentially another option as well, which could be rather clever, but then it's more inconvenient to use this smallest function. You need to separate whatever you have into the first thing and then the rest of it, which, you know, there's different trade-offs to consider. This is part of why like design is a big consideration in this course. You got to, you know, think about what's the right trade-offs to make in the situation, right? All right, blah 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 blah. John Smith, yep. Yep. Okay, cool. So let's just do it this way with an option. And we'll say, you know, if x is empty, return none. Maybe the better way of doing this is like, you know, we could match on x's dot first, right? If it's some element, then do something. If there's no first element, then we can just instantly spit out none. And if we know this, if we know we're going to instantly just return none if there's no first element, then what could we write? We could say let first equals x's dot first question mark. Screw this whole match, screw the is empty, whatever. If the first doesn't exist, the question mark will bubble that none up and just like return it from the function immediately. But we know that if it does exist, first will not be an option anymore. It's just giving us the t that we care about here. So that's pretty good. And then we could say for item in, let's make this mutable, I suppose. For item, let's call this like lowest as well, as opposed to first, or smallest, I think was what we were looking for. For item in x's dot iter, but we want to skip the first thing. If the item is less than the smallest, then the smallest is the item, and then finally give back whatever the smallest thing was. Now this is no longer happy because we have a little bit of a potential problem here in that I've now sort of made this work over borrows to t, but I've told it it'll return back a t itself. So we could just go like, screw it, we'll just return a borrow of t. Then we have to think about lifetimes and suddenly things are a little gnarly. Or alternatively, I can do like an IntoIterator and the code's going to become a little more complicated. This is a very like Rust moment where it's like the obvious thing here, the easy thing is not working because ownership moment. And so I would probably write something like let mut iter equals x's IntoIterator. Let the smallest is iter.next. So just give me the first thing in the iterator, and then for item in the rest of the iterator here, like that. And now we're all happy. So turn our vec here into an iterator. The smallest is I'm gonna assume the smallest thing is the first thing. If there is no first thing, if the iterator returns none, then just return that none upwards. If it does get something, that's great news. We now have the smallest value as a t, because IntoIterator as opposed to iter or iter mut. Then for item in the rest of this iter, notice we've already got the first thing out of this, so it's not going to yield that first item anymore. We've already sort of notionally skipped it, I suppose. If it's less than the smallest, that's now the smallest, and then just give the smallest back at the very end. So this is a perfectly reasonable implementation of this, and in theory, it should still work with the rest of our test cases. So let me grab this. Let's do, square bracket, and square bracket, and test it. Right, 142 is 42, 314, 99 is 314, A, and then a student here. And the great thing is if I throw more numbers into this, 1,000, another 42, a 7, and a 600, just random numbers, our function still continues to work and gives us 7 back. Right, so that's pretty cool. But it is, notice it is like wrapped in an option, sum of blah, sum of blah, sum of blah. Which, you know, is a little, potentially a little painful, but we've made our function more generic. Now, there's one more thing that I want to quickly talk about before we jump into the break here, which I'm going to, you know, ask the chat in this case. X is here, right? We've taken an x's, and I've just said it's going to be a vec of t, right? I've said it's going to be a vec of t. Now, there's sort of a fundamental shift in the way that I want you to think about like a parameter to a function and like types and stuff for just a second. So when we say that like my function here, x, this function takes in parameter x is an i32, right? Why did we make x be an i32? In this case, it wasn't really for any good reason. I mean, there was a couple things. i32 we knew implemented ordering, like partial ordering, so I could do this thing on it. And the other constraint really was that these two things were the same type as the return value. What's maybe a better example? Something like, let's say function log2 or whatever. And I take in an i32 and I spit out an i32. The types might be a little gnarly there. But I think x has like a log2 function I can call. A u32, I guess, is what I'm looking for here. And this is probably unstable, so don't worry about the error message there. But my question is, why did I choose x being an i32 here? Well, I imposed this restriction, x is an i32, because I needed to call log2. And log2 is only going to work on some kind of number. And so I need to impose the restriction that the x I'm taking in here is a number, right? If I just made this any type t, then this is just not going to work at all, because it's going to go, what do you mean by log2? Like log2 is a function that only exists on a subset of types. So I impose the type i32 here because I know that an i32 will let me call log2, right? Now we come up here and try and apply the same thinking. I've imposed x's to be the type vec of t. Now t has its own restrictions that we've already thought quite heavily about in terms of finding the smallest, which is that t can be partially ordered. We need that to do this operation down here. But, so if we forget the t for a second rather, why did I impose the type vec? what is the only thing that sort of Vec is bringing to the table here? Aha! And actually, Andrew, I'm just catching up with the chat, and Andrew seems to be like on the money here as well, and people seem to be catching on quickly. But just to like really spell this whole thing out here, what is Vec bringing to the table here? Well, Vec, right? If I look at where X's is used, Vec implements IntoIter, right? Vec is a thing that can be turned into an iterator, right? But where did IntoIter even come from, right? If I search up, if I go to Vec and I look for the IntoIter method, yeah, okay, stream's okay. Stream is healthy, okay, very good. Apparently the stream was unhealthy for 2 minutes, so I think that's okay. And we look for IntoIter, where is it? Insert, into box slice, into flattened, raw parts, blah, blah, is empty. No IntoIter, that's weird. If I keep scrolling down, blah, 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 blah. I'll come to trait implementations. What traits does Vec implement? And as part of that, I'll find an IntoIterator trait, right? We're looking for this implementation here in particular. It says implement IntoIterator for Vec. What does that give us? It gives us a function IntoIter, right? So as the chat is noting here, this like Vec of t is needlessly concrete is the way we would say this. It's needlessly concrete. There's no reason that we need to use a type as specific as Vec, right? No longer need to be a type as specific as Vec. This could be more generic. So, and like, what would this let us do? Well, what if someone wanted to like, had like a linked list, say, a linked list of values as opposed to a Vec, or they had an array of values, right? Or they had like a hash set of values or something like that. There's all different kinds of containers that someone might have containing t's that they want to find the smallest element in that just aren't a Vec. And by writing Vec, we're forcing them to take whatever format they have and shove that into a Vec just for us to turn that back into an iterator. There was no need for this to be a Vec. So how could I write this? Well, we have our type parameter t. We may also want to be generic over some container type. I'll just call it I in this case, right? I, because it's going to be turned into an iterator. But if x's is no longer a vector t, we could make x's some I here, where I implements the IntoIterator trait, right? IntoIterator. If we look at the trait here, you'll see when it loads, there we go. IntoIterator defines that function here, and it also defines a type. This is one of the first things where, like, you know, a big difference between, say, Java and Rust's Java's interface system and Java's interface system and Rust's trait system have a potentially significant divergence. I think Java might be introducing, this is called an associated type parameter. I think Java might be looking into this, but I don't know how far along they are with that, if at all. But we have an associated type parameter here that says when... okay, hang on. It's only just a little bit. It's happy again, I think. Hotspot moment. Yeah, hiccups. Okay, it's green again. I think it's okay. Yeah, it seems it's a little bit iffy, but we'll take a break in a minute anyway. It defines this associated type item, cool, which is what item will this iterator that it can be turned into spit out. I'm also going to stop the playback on the preview because that might be sucking up some internet potentially. And so we'll just define that here. We'll say that I implements IntoIterator where the iterator that it can be turned into will spit out items of type. What items, what type of items will this iterator spit out? I'm assuming the chat's going to catch up with this, and you're probably right. T. I'm hoping that you've typed in the chat. It'll spit out T's, right? Yay! The chat did get there. Great. I predicted it and everything. How amazing. Exactly. So now we're sort of like very generic. This function takes in anything I, any type I, where I can be turned into an iterator that produces items of type T, where T is any type such that it implements PartialOrd, and this is like a really just beautifully generic function, in my opinion. And you'll see this just works, right? It still works because if I do x's dot here, you'll see what information does the Rust compiler know that x's has. It knows that it has IntoIterator because we've defined that constraint here. It doesn't know if it has if it can be turned into a string. It doesn't know if it can be, if it has a default value or anything like that. The only constraint we provided was that it can be turned into an iterator that produces T's. So the only thing available for us to use is that it can be call the IntoIterator function that the trait defines. And so this just beautifully works. We'll test it. We'll take a break. So if I have let L is my linked list, mutate, and I'll say L.push to the back. I'll push 42. I'll push 100. I'll push 5,000. And I'll push 7. And we'll print out smallest of our linked list here. And that would be, the smallest of the linked list was 7, which is great. What if I give it smallest of a reference to L? Smallest of a reference to L is still 7. Wow. How did that work? I didn't even have to move it in. This is like a lot of trait implementations helping us out in Rust that the standard library has written for us. In particular, what it's inferring here is that the item, the T here, is going to be in fact, I might type this out, is going to be a borrowed I32. That's what T is. And I here is going to be it's the linked list really. It's a ref linked list of I32s like that. And it knows that a borrow of a linked list of I32s can be turned into an iterator where the item is it's going to infer T here. So item is, right, yes, where the item is a borrow of I32, right? We saw that T here is I32, item is T. So, oops, I've lost it here. So it will infer this. And then the other requirement is that T is PartialOrd. So a borrow of I32 is PartialOrd. And all these things are sort of defined in the standard library all over the place. I could quickly point you, say for a linked list, you would find that IntoIterator is defined not only for a linked list, where it'll give you an iterator of T's, but also is defined for a borrow of a linked list, where the item is a borrow of T's. So that's what gets us sort of halfway there. And then we also need to know that borrows of I32 can be ordered. And if I go to something like I32, which is just a big thing here, and look at partial orderings, PartialOrd, you should find that, in fact, maybe PartialOrd itself has this, let's see, PartialOrd for, there's all kinds of things here. I32, how is it inferring this? It's inferring that it can order borrows of I32s, but in my lecture mode right now, which is I can convince you whenever you're sort of up in front of everyone lecturing, you sort of got to at least halve your intelligence in front of the crowd. But it's able to find that it can partially order borrows of I32s, but my brain's not finding it at the moment. But hand wave, it figured it out. It's pretty cool. But yeah, so it's just like a function that can be used with all kinds of different values, specifically because we only specified the constraints we cared about, right? Just as a really quick reminder, if you went, I need a function, I have a vec of I32s and I need to be able to find the smallest thing in that, you could very well just go smallest v is my vec of I32s, and I'm going to spit out an I32, and you just write the code here. But if you think, and that will work, but it's needlessly restrained. it's needlessly constrained, right? Or needlessly concrete. If you take a little bit of time to think about what are the actual requirements I care about, then your code will work for like anything it possibly could on, which is a very powerful idea. Let's take a break. Let's take a break. We'll come back at 20 past. We're really in no rush, to be honest. We have all of Wednesday's lecture as well to keep moving on this stuff. But I think we're going great so far. Yeah, let's come back at 20 past, have a little break, and we'll see you then. I might answer some questions in the chat or something like that during the break. But enjoy your break. We'll be back at 20 past. All right, so let's get back into it. Oh, actually, I was worried that the green screen looked like it was doing some weird stuff. Let me just muck with the lighting a little bit. That seems about okay. Oh, yeah, sometimes it starts thinking my shoulder is green or something. If the green screen gets distracting, I'll just turn it off. So if you're finding it distracting, just let me know. So Right. Yes, the chat was talking about the multi-crate submission. I probably should have mentioned this at the beginning of the lecture, to be honest. Give really hates the idea of submitting like files that are like non-fixed, let's say. Because like we don't care what files you write. Like if you want to split it up into 50 different files, or if you want extra like data files and stuff like that to do things with. So we didn't want to impose that restriction, right? You can almost think of it as like what we're doing here. And so we get you to submit tars, but dealing with tars and stuff is kind of annoying at best, I suppose. Just because, well, yeah, it's just kind of annoying to deal with. So we provided things like 6991 auto test and 6991 give to automate things for you. But when I wrote that tooling, I didn't anticipate having to deal with multiple crates at a time. So time to use GitLab, yes, but then you have to bring in Git for people, and not everyone wants to use Git for every single like exercise. And so, probably what we're going to do is on specifically the things with with like multiple crates and stuff like that, we'll do basically what you wrote in the chat there, Andrew, which is get you to, sadly the tooling might not be advanced enough for this, tar up your things manually and then submit the tar. I'll probably write some instructions for that up probably after the lecture, otherwise maybe earlier tomorrow. And we will make an announcement and send an email. We'll make an announcement and send an email when that's all, when we've figured something out for you. And our deepest apologies as well to go along with that. So there was a question, which was, is there a way we can make it more clear what the constraints on X's are in the definition as opposed to down here in the constraints? And yes, Rust does have a shortcut for this. Since the only constraint on I is that it can be turned into an iterator where the items that it spits out are T's, then we can just do that in line. So there was two ways we sort of sought to do that. Well, there is two ways to do it. We saw one of them. One is that we can just sort of inline say I is something that can be turned into an iterator where the item is T's, which is like maybe halfway to what you want, Miguel, but like not quite there. But there is one other way that's a little better. Note that as well that T, even though T does only have one constraint on it, it also does impose a second constraint, which is that the item that the iterator spits out is the same as the T here in the return type. So we can't do the same trick with the T, but we can with the I, because it's only really like just, this is the only constraint on it. We can remove the I as a type parameter at all. And then instead of saying X's is I here, we can use this special syntax Impl, where we say X's is some type that implements into iterator where the item is a T. And this is probably much more like your Python sequence of blah inline. And you may also prefer the syntax. If I run the code, you'll see everything still works amazingly. But notice if I tried to replace the T here with, if I tried to do the same trick, T is anything that implements PartialOrd, well, that works in the context of X's. But then the question is, what is this T here? I can't really say that this T here is also Impl PartialOrd because what's the relationship between this and this here? It's not actually given that the item that your iterator spits out is the kind of item that you'll return out. That you put into the function is what the function will give back. The only guarantee this function gives you is that it'll give you some type that implements partial ordering. And so the only thing you would be able to do with this thing that got spat back out at you is order it with other things. You can't do the same trick with the T in this case because there's too many restrictions going on. But in the IntoIterator case, you absolutely can. And that's what we have right here. So hopefully you enjoy that. Hopefully that tickles your fancy for what you're looking for, because that's about the best you're going to get in Rust, sadly. I can't think of any shorter shorthand off the top of my head than this. Could we keep the OG code scaffold in the repo and submit it with the additional 2 crates? Yeah, that seems fine as well. It's not, if I recall correctly, it's not an auto-marked exercise. So like, at the end of the day, I'm not really that fussed how you end up submitting the stuff. So yeah. Cool. So that's type parameters. Note that type parameters can go on, not just on functions here, but they can also go on struct and enums and that sort of stuff, like we saw with lifetimes. Our easiest example here being option of t, where there's either some t or there's none. Right. But something to keep in mind is that when, if I wanted to add a function to this option, let's say a function that's like is none or is some or something like that, as I notice myself phasing into and out of reality from the green screen, I can't simply write impl option anymore. Impl option function is none, takes a borrow on self, returns a bool, match on self. If it's sum of something, then return false. If it's none, then return true. Something like that. This won't work anymore because option is not really a type. This is something maybe I should have mentioned a little earlier, but whenever you have a type parameter, you can almost think of this function here has parameters that need to be passed in. In particular, it has this x's value that needs to be passed in. But you can almost think of there's a step before that where the smallest function takes a type as a parameter, right? This smallest function requires a type t before you even get a function at all that you could pass a value to as a parameter. So that's why we really call it a type parameter. And that's what's happening here, is that option is no longer a type. You might, if you're going full sort of PL mode, you might even like to think that option is almost like a function on types, where option alone is not a type. It's more like a function where you give it a type t and I'll give you the type option of that t. And so I could say implement only for options of I32 this is none function here, and this would potentially work. It's probably pissed off because why are you? Oh, you're upset because I need to say, that this is a option sum, option none, like that. But that's needlessly specific. This should be able to work on any option. And so you can also say implement for any type t on option of t, right? Same sort of idea as before. For any type t, we implement on an option of that t, the function is none. Or you could say something like impl for any type t on option of t, where t also implements default, something like function unwrap or default, which will give you the t, such that we match on self. If we have some t, then we give that t back. If it's nothing, then we just give the default value for whatever that type t is. And again, I've got the same stupid problem here, like that. Like that. And this will work for the same reason this function down here works. Apart from the fact that, that's funny. It's because I've called this option, it's getting the two options mixed up and it's broken everything. But this is essentially what the definition will also look like in the actual Rust standard library for this function here. So impl t option t, where t is default, this gives us the constraint that the default function will exist for the type t, which is what we're using here. And we just write the method as such. So yeah, this is something to keep in mind when you're doing implementations. You can also throw generic type parameters here. You can also specify constraints on them, so forth. And I'm looking like I got Thanos snapped. Yes. Why would the impl be necessary? IntoIterator isn't a defined type constraint, so the fact that it's a whatchamacallit interfacey thingy is pretty clear, right? So yes, that's certainly partially true. The things that I would sort of point your eyes to is, A, if there was no impl here, sure, the compiler could probably see this and go, that's a trait, so I know what you mean by that. But if I'm a human reading through source code, is it immediately obvious to me that this is actually generic? like it's generic over T, but is it immediately obvious that this is also like a generic type parameter in its own way? Because to be clear, this Impl IntoIterator just is syntax sugar to turn itself into, you know, I, this is an I where I is IntoIterator and so on and so forth. So like, it's almost like a hint to any reader who's looking at the function that, by the way, this is generic. You can use all different kinds of types here. It's not some like struct IntoIterator. So that's one thing to consider. The other thing to consider is something you may not be able to entirely consider yet, which is that this is one sort of method of working with generic types and traits and stuff called static dispatch. And we are going to learn about a completely different way of dealing with traits called dynamic dispatch, where this impl here is actually going to get replaced by dyn, dyn. And so there's multiple ways of working with traits. So the impl is sort of helps make it clear what's going on, I suppose. So reserve judgment for now, and then once you sort of have a bigger picture of everything, you can ask yourself that question again, I think. Do all these impl blocks stack together so you don't need to redefine some things? Yes. So these all sort of get just thrown on the option type, but you know, some of them might have different restrictions on that T. So for example, you wouldn't want to put is none in this block here because you're also implying the constraint that this function can only exist where T exposes some kind of default value. But like they all end up on, you know, if you have an option of I32, since I32 has a default value, you'll just see both of these methods available to you and things will just work essentially, which is quite nice. Okay. I am continually looking like I'm getting pretty Thanos snapped, so I might try and really quickly filters, chroma key. Is there a way to just I'd like to turn it off without just deleting it. I suppose I'll just delete it for now. I can always make it later. All right, you'll get an actual background for now. I gotta get this thing. Oh, so welcome to new background. Bloody hell, that's a big green screen. It's funny because the new walls are also green, but I don't think the most effective green screen. If the camera gets in the way of something, just let me know. But it's, yeah, room reveal. Study reveal, yes. Cool. It's so neat that you can have methods that only appear based on the contents of the struct. Yeah. Cool. Not the first lecture I've seen with a door behind them. Okay. So let's catch up with the slides. Smallest value, we saw that as the very beginning. We made it generic over any type T that can be partially ordered. Then we made it generic over any container type like a vec or whatever. We started to talk, you know, about different traits and stuff. And I think, yeah, a nice spot maybe to sort of, well, we'll see how we go, but, you know, 20 minutes or so, we can just poke around at a whole bunch of common standard library traits and how they work, and then save working with traits and trait objects and stuff maybe for Wednesday. What's behind the door? Another door. Yes. Okay, so there's a few different categories here, and these are stolen from where are these? Where's this sort of like general listing stolen from? It's stolen from like rusted traits, Rust, here, the Rust blog, that's the one. Tour of Rust standard library traits. This is a great little markdown file that is loading slowly, but the stream is still healthy. Okay, yes, good. That has, you know, a whole bunch of information about how traits work and different things traits can have and all that, and then takes you on a tour through all these different kinds of traits. I've left a, you know, not an obscene amount, but quite a few of these different traits out that are just like needlessly complicated or not sort of interesting for what we're looking at now. But I thought it would be nice to have a little poke around and see like different traits that the standard library defines. And why is it good? Like, why might we be interested in specifically the standard library defining some trait? Does anyone want to give some thoughts on that? Like, for example, the default trait here that specifies, I think we were just looking at this before actually, that specifies that some type has like a canonical default value, like a a general default that makes sense. Why is it specifically useful for this to be defined in the standard library as opposed to just in my code base that I wrote? Miguel says it means that it'll be consistent between all apps. Yeah. And I'll substitute the word apps there for crates, but meaning the exact same thing. Like even if we have two traits called default that are like the same thing, like if I write trait default, which just defines a function default that creates, like that. Also, I'm going to comment out this option because it's driving me nuts. Like that. Even if I define a trait default that looks like this, it's not going to be the same default. This is not considered to be the same trait that's defined in the standard library, right? And if it wasn't in the standard library, let's say there's like 10 really popular crates that all define this trait default. Now none of those defaults are actually the same, which is kind of annoying, right? It's kind of painful. So if I just went, I want any type that has a default, like in this option here, right? This unwrap or default function that just requires that the T should have some sort of reasonable default value. Like there's no sort of like, what would you say, consistent way to make that work. There's no sort of there's no really generic, really is probably the right word for it. There's no generic way to make that work across all different sort of types that anyone might want to use in my crate. And so it becomes really difficult to sort of establish these sorts of like points of commonality almost between these different crates. Who should be sort of responsible for the default trait? So like a really good example of where sort of we have to think about this is if I am in the standard library here and I go show me the serialize trait, the trait for any type that could be serialized into bytes. 0 results found, no results. You want to try on DuckDuckGo? Sure, let's try on DuckDuckGo. And we'll find, there it is, a couple down. Thank you, DuckDuckGo. Is that this trait exists in a crate called Serde. S-E-R-D-E. Huh, that one's familiar, right? Serde serialize. And so the standard library went, this is too big of an issue for us. And like, there's a reasonable chance that we get this wrong. Like we do our best at making a trait to serialize things or deserialize things, but it's like not, like the community wants something more powerful, more generic. And, but like we're the standard library, it's really hard to change things because we need to make sure we sort of maintain backwards compatibility and everything. So they went, let's not do this. Which means there's kind of an arms race. Like there's a race to who can make the best serialized trait that everyone's going to use. And the thing that's really annoying, potentially, is when there's two really big crates that like half of the community each use one of these crates. And then you like need to build all these sorts of layers of compatibility between the two of them just to make life not be hell. Fortunately, in the case of serialization, Serde like just hugely won out. Everyone loves Serde. If you don't love Serde, then we'll bring out the pitchforks and the flaming torches and stuff. You know, Serde absolutely won out in the war of serialization. And so yeah, like this ended up being okay because everyone, if you want serialization, go to Serde. But there are scenarios in which this has been an actual pain. In particular, in async Rust, there's two primary asynchronous runtimes. One's called Tokio, Tokio, and one's called async underscore stud or async dash stud. I always get it backwards. I got it right this time. Async stud, because they put a bloody dash in their logo. And these days Tokio is winning out over async stud, it appears. But it's, you know, there's still people that use each of them. And so a lot of workers, you know, people who need to be generic over the idea of their program being async often need to provide two feature sets in their program. Use this stuff if you want Tokio, use this stuff if you want async stud, and it can be a real source of pain. So really sort of generic big picture ideas we really do like to have in the standard library because we get uniformity across the whole ecosystem. So let me catch up on the chat. You don't need to add boost : to everything. Consistency, C++ moment. Suppose it wouldn't make sense the default is not the default across all defaults. Very good. Was that site suggesting DuckDuckGo was your default search engine because of some partnership? I think it's because like a core value of Rust is, you know, the ability for privacy and stuff, and so DuckDuckGo is like a relatively, at least, sensible default for that. I'm not 100% sure. I don't think it's because it's my preferred search engine, because it was, and then I changed back to Google because I think internally DuckDuckGo is Bing, and Bing is sometimes doesn't get me exactly what I'm looking for, which is kind of frustrating as a developer. This reminds me, what casing should we be using for file names and directory names? Do you mean for, right, like for source files and source folders? We generally use lower snake case for all of that. So if I have like, if I make a new folder, my module, then we use lower snake case, and like my file in module.rs, something like that, we use lower snake case, all of that. It's specifically in types and stuff where we jump to that upper camel case over here, like PartialEq or PartialOrd, or IntoIterator, yeah. And yes, there's some kebab case, but there shouldn't be kebab case for modules or file names, or I think sometimes people use kebab case for like crate names, and that's annoying to me because Rust doesn't like kebab case, because kebab case, yes, is written how they've done it there, because there's sort of an ambiguity between if I write my dash module, is that a module named my dash module, or is that a variable my that is subtracting a variable module? And so because it introduces the ambiguities, it's generally not permitted in the Rust language. Anyway, so there's one more thing I actually really wanted to mention, and then we'll just go on a browsing spree and like we'll have a chill final 10 minutes or whatever. The last thing I also really wanted to mention is, how does this even work? Right? That might have been kind of good to know, right? Like we wrote stuff like this, and this was like, we've gone sort of way off the beaten path here in terms of making it very generic, and it's very cool and we love it. But let me just go back to what we had before, which was like smallest, I'll just call it smallest 2, because we had two things where x is a t, y is a t, returns a t, also where t is PartialOrd. There we go. And we had if x is less than y, then return back x, otherwise return back y, like that. This is where we were at here at one point, and hopefully we should be comfortable with the idea of this. How did this even work? If I have some function foo, and that function foo calls smallest 2 of like 42 and 100, and then it calls smallest 2 of 42.2 and 100.1, and then it calls smallest 2 of x and z, how does Rust make this code work? Right? You might have an idea in your head of like, oh, that's obvious, but it shouldn't be obvious, because there is many different ways you could implement this. So how a lot of languages, a big chunk of languages choose to implement something like this. So let's say Java has a strategy that's quite similar to this. We dropped to 6K bit rate, but I think that should just be like quality drop, not straight up outage, and it's back. I think it should be okay. The Java will attempt to do something like this by generating one function that's called smallest2, and it deduces how to like do the body of the function based on like it'll check at runtime in a certain sense. This is a little like hand wavy, and it's more complicated than I'm making it out to be, but essentially we'll go, is x and is t an i32, is t a float, is t a character, and it'll do different things in the body based on, you know, what type t is that it figures out at runtime. This is because Java has a concept of types at runtime. Right? at runtime, you're able to figure out if I'm like a type foo or type bar, or like if I'm type animal or type dog or type golden retriever. That information is still available while the program is running. And it uses that information to deduce how the body should work, generating a single smallest 2 function. The way we've written it here, Rust does not do this, right? Rust does not take that approach how we've written it here. That is an approach called it's dynamic, right? That's a dynamic dispatch at runtime. And it's what we're going to look at later on with, I mentioned earlier, there's something called the din keyword, right? Where we have some like din PartialOrd, whatever it's going to be. And Rust doesn't do that for one. There's a few quite good reasons, but just to like rattle a couple ideas off, dynamic dispatch takes time, right? It takes time in that when you call the function, some work has to be performed to figure out what type it is and to sort of do the right thing based on what type it's being called with. That takes performance. It also harms the idea of optimizations because you can't optimize this function for any particular type T. You can only just sort of like apply optimizations that would make sense for any type T that might be used because you don't know what type the function might be called with. So how does Rust avoid this? Rust avoids this with a technique called monomorphization. Monomorphization. That's a tricky word. And this is the same thing that C++ does with its templates. The way monomorphization works is, believe it or not, when I call smallest 2 of 42.100, 42.200, smallest 2 of X and Z, it literally spits out these 3 functions. It literally spits out these 3 functions. When the program is being compiled, right, when I'm running Rust or cargo build or cargo run or whatever, you are correct. So dynamic dispatch is how C++ implements polymorphism via vtables. Virtual, yes. Which is the same idea as din in Rust, dyn. But templates in C++, template expansion is done monomorphically, which is what we're looking at here. So when we have this function here, smallest 2 of t, no smallest 2 function ends up being generated as actual code. Instead, Rust will inspect anywhere where this function was called. So it'll find it's called here, here, and here. It looks through the whole crate for this. And it says it was used here with an i32. It was used here with a f3264, I don't know, whatever it decides it is. And it is used here with a char. I think actually this would be f64 in particular. So it finds, okay, it was used with an i32 and f64 and a char. And what does it do? It literally takes the function here and spits out smallest 2 i32. And it finds all the t's and goes, yep, that's an i32. Yep, that's an i32. Yep, that's an i32. And then spits out this code here. And then it does the same thing for f32 and for char. f32, 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 f32. Oh, sorry, that should have been f64, but you get what I mean. And it does the same thing for chars. And we are right back where we ended up. Right back where we started, I should say. Right? It's the exact same stuff. And the reason this is potentially better in terms of the trade-offs we were looking at earlier is that now the compiler is free to optimize all these functions individually to make them go really, really, really fast. Like maybe there's a trick with i32s or a trick with floats where you can check the ordering really easily. And in fact, there actually is really clever tricks on floats to check ordering very easily. You might have to head to 1521 for that and look at, there's like a solution I wrote to float ordering lab exercise at one point that I use a very, neat little trick to order floats quite cleverly. Now the compiler is free to make those optimizations to make the code run very fast. And it's also free to go, hey, this is just being called with like an i32 here. That's just this code here, which is very simple. I could just like take this function call and spit out this code right here, which is called inlining. And it goes, okay, it was called with 42 and 100. So I'll just substitute out 42 for X. I'll substitute out 100 for Y. And then, oh, I can figure out exactly what this is right now. Is 42 less than 100? Like the compiler, the code's not even close to running yet. It's like, I know what this is like statically, so I can just turn this into 42. And so probably before our code is even like built, it's already just turned this into like 42. It's already just turned into that code there. This is something that compilers do liberally. And this technique is called inlining, where it just grabs the body of the function and pastes it in if the body is like simple enough. And so it's very clever like that. It's tangentially related to const_expr, but there's some more stuff that goes on. And Rust has const functions as well, which is a similar sort of idea. But it's a similar idea in terms of trying to get things to go at least very fast at, when we actually have run the code. So there is obviously, there's trade-offs to almost every decision that we make. And can anyone think of a trade-off, like a negative trade-off of monomorphization in this case? There's two sort of really main primary trade-offs that I can think of. But this technique of just going, find like where it's used, for like find out what types this function's used with, and just for each of those types, spit out as an individual implementation for that type. Right, number one, and this is absolutely probably the big number one, as Dong and Andrew and also and Patrick here. In fact, let's say there's three, because that's a really good point as well, is the program size. Like once we've compiled the program, how big is that binary? Monomorphization in particular makes that program size, once it's compiled, get bigger and bigger, because if you write one function that's called with 1,000 types, you now have 1,000 functions, as opposed to something like dynamic dispatch, where you do a little bit of extra work when the function is called each time, but there's only one function. And so, if you're using just one type, like if it's only called with one type, maybe monomorphization will net a smaller amount of code. But if it's 2, 3, 4, 5, 100, 1,000 types being used, then dynamic dispatch, which only generates just a single function like what Java does, may give you a much smaller overall program size. Yes, Josh also mentions libraries have to be provided as source code. And with this no work for shared library, yes, that's what you're both saying there. I'm going to say it a little more generally, because that's sort of like maybe one step further along from the way I'll put it. The way I'll put it is, with monomorphization, you must know what all the types are at compile time, right? Like in Java, I have a function foo that takes in A is some animal type like this, but realistically, this type could be all kinds of different things. It could be someone could call this with a dog, someone could call this with a cat, someone could write a completely separate Java program that loads this program in and provides an animal that this program had never heard of before, assuming they, create their own animal that extends the thing, whatever. Like this function can take all kinds of different types that it may not even know exist when it's being compiled, which is just not something compatible with the idea of monomorphization. So I guess the three big trade-offs here would be the overall code size, slower compile time because there's just more code to compile often with monomorphization, and number three being you must know all the types at compile time, which is not something you'll always know. Because of that, we're going to look at doing dynamic dispatch, right? Which is sort of a different way of providing this generic behavior without monomorphization, and like specifically without knowing what types things are at compile time, where we'll pay a slightly bigger performance penalty in running the code, but we won't we won't have those trade-offs of code size, compile time, and knowing all the types at compile time. And that'll be on Wednesday, though, of course. We don't have time to cover that in about 30 seconds of time. And if you've heard of things like vtables in C++, then you should be familiar with the idea of dynamic dispatch already, because that's essentially what we're looking at with din in Rust. Cool. So that's how this ends up working. And I guess I'll just undo to the point where that was kind of sensible, which was here. Everything still compiles and builds. So I think that's a good point to upload this code to GitHub. Yeah, there's a whole bunch of random stuff there for you to poke around and play around with for sure. I guess we don't need this though. I said we take a tour of the standard library traits, but we can leave that for Wednesday. There's really no big deal in that. But if you want to poke at the slides yourself and just like for each of these traits that I've written here, let's say, for example, display, that's a cool trait. You just go to the standard library docs, which you can either access by clicking on Ferris up here or just going to docs.rs/std. It's good. And then search for that thing. So I said display, I think. You search for that. Look for the pink ones. The pink ones are traits in this case. Wait, no, that's wrong. This is a struct. You lied to me. Sorry, not purple. Blue. Blue, sorry. Ignore what I said. Blue is traits. I mean, it says trait over here. And so we find the trait and you go, what does this trait do? Display is similar to debug, but display is for user-facing output and cannot be derived. And it shows you some examples. Try and figure out what these different traits are for, how you might implement a trait yourself. But otherwise, we're going to play around with them on Wednesday. Alrighty, so any questions? I'll cover this question in a second here, but we'll call that official end of the lecture. Feel free to type out any questions you have into the chat. And so let's see what Patrick says here. Do you mind just quickly elaborating on how creating new types at runtime would work? Is it just your program accepting user input to construct a new type? So I think this is in the case of the Java one I said. And if you can follow along with a bit of syntaxy hand-waving stuff, you might have something in Java that's like class animal, right? And a class animal might have a string name and a function, maybe void speak, which is able to say system.out.println blah blah blah, which is able to say my name is name and I go blah, I don't know, whatever. And then you might have a bunch of other functions, classes that extend off this. Class dog extends animal. And it might define its own behavior in here, in fact, I will speak like such. I'll say, my name is blah, and I go dog. No, I don't. I go woof, rather, I should say. And so on and so forth. And you might write a function in your Java library that's void say hello to animal that takes in an animal. I'll call it animal. And what does it do? It goes system out print line, print to the console. Hello there. Hello there. Animal.name. And then the animal might speak back to you, right? Something like that. Now the idea is you've written this function here to work on any animal, and it knows sort of the things that are available on this, right? What sort of what properties and behavior an animal can specify. And the idea is someone could pull in your Java library as a library into their program. So now we'll say this is in my program up here. Up here was the library. And in my program, I could write code as such. I could say class, what's a cool animal? What's someone's favorite animal? I'll do maybe a lion or something. Right? They could, assuming the visibility all works out, public, private, whatever, they can make their own animal. It says, my name is blah, and I go raw. Right? Actually, that should be like this, shouldn't it? I'll leave it like that. That's more fun. And they could, in theory, still call your function with their lion, or whatever it is, and your function will still work. Right? Your function will still work even with this lion. All right. Turtle is in full caps. Sorry, Dong. CC went full caps, so I'm going to go... Well, what does the turtle go? It goes I'll just do crickets. It doesn't make any noise, I guess. Anyway, the main idea being that you could say hello to animal with an animal that this library has never even seen the likes of before, and it will still work. Why will it still work? Because the function, when it goes animal.speak, is going to look sort of at runtime how do I say this? I'm trying to I don't want to go too deep into the weeds and just become needlessly confusing. Yes. Yeah, right. Yes. So this would still be possible via monomorphization if the creators provided a source code. Yes, absolutely. But if you don't have all the source code to compile all at once, then monomorphization won't work here. Now, there is one sort of canonical example of when you don't have the entire source code available all at once, which would really impact this scenario here, which is something like a plugin system, where the library is no longer library. Let's say it's like the server, right? And this is some big server that's doing does a lot of work, and it's such a big idea that you might want people to be able to extend the functionality of this server with additional behavior, right? But you want it to sort of be like swappable, these sorts of additional behaviors swappable in and out. And this is sort of like a pretty big contender for like the like plugin pattern, right? Where essentially you have this primary thing, the server, and maybe when the server's booting or something, it'll look up for these dynamic libraries. Yes, as you mentioned there in the chat. In this case, we'll call it like my plugin here, which adds more types and does more stuff, but the server's already been built and compiled by this point. It's like, in fact, it's even running by now. It's booting up the server. It discovers your plugin and wants to load the code into the current environment. And so it's too late for monomorphization. So this is like a scenario where you really might care about this. And so you have to lean on something like dynamic dispatch, which Java has like dynamic dispatch everywhere. Whenever you're calling a function in this sort of way, like a function on an object like this, it's dynamic dispatch, which is why Java is not really in the same leagues as something like C, C++, or Rust when it comes to performance. Java can be very fast. And in specific scenarios, Java can even, once the Java's virtual machine gets like warmed up and starts applying on-the-go optimizations, it can even potentially run faster than, carefully tuned C, C++, or Rust code. But just in general, Java's not on that same sort of performance tier as like on-the-metal languages. And this is a pretty big reason as to why. Java loves to malloc all kinds of stuff. It boxes everything it can, and basically almost any function call ends up being dynamic dispatch. Even this print line here will end up being dynamic dispatch, where in Rust you're usually a lot more sparing with it. Part of that admittedly because there's some pain that comes along with dynamic dispatch that we'll talk about on Wednesday, but it's a consideration regardless. And how can Java make itself faster? As Miguel was mentioning there, through JIT compiling mainly, which is JIT stands for just in time, where as the program's running, and JavaScript in particular often has these kinds of optimizations as well. As the program's running, it sort of looks at common patterns and modifies its own code, as it sees fit to try and improve the performance. And occasionally, it's getting sort of like current runtime behavior information in order to optimize the code. It might take quite a bit of time for it to figure out those right optimizations, but once it's applied them, you can get faster than, carefully crafted C, C++, or Rust with the power of that. But again, it's pretty specific, and it's hard to be very general about these kinds of things. Apart from just being like, generally, it's not quite in the same performance tier, but it always depends. Best animal is an otter. Sanest student in chat right there. Polymorphism, dynamic libraries, OS extensions, design patterns, C#, Java, Java, Microsoft Java. Yes. Operator overloading. Yes. C# is, from my point of view, Java, Microsoft's, competitor to Java, but also with like more bells and whistles attached. To put it very briefly, and what's the word I'm looking for here? To put it briefly and I can't find the word I'm looking for. It's escaping me. like briefly and a little bit like a bit of an idiot is what I'm trying to get to. But there's the right word for what I'm looking for. But yeah, it's not the differences are never as simple as that. But it's fun to put it that way to just answer it quickly. Okay, cool. We're talking about all kinds of random stuff, and I'm glad for you also to be doing that. But do we have any other questions before we end the lecture off? I'll leave time for any questions about our content and stuff, I suppose. Otherwise, you can just keep chatting. I don't really mind either. I'll probably close this because other people might be confused as to why that's just randomly there. See you later, Cece. No worries. Any other last questions? And we've got some fun ahead of us for Wednesday as well, naturally. FizzBuzz Enterprise Edition. Yes, I know FizzBuzz Enterprise Edition. Imagine we had a course Discord. Well, you could make a discourse thread and chat there, of course. For anyone who wants to see FizzBuzz Enterprise Edition, it's pretty funny. It's pretty good. It's this first one here on GitHub. It's a very, very Java moment FizzBuzz implementation. Just, enjoy this in your own time. It's very funny. Okay, anyway, let's call it there then. I'm not seeing any other questions. So thank you everyone for coming. Hopefully we had some fun, and we'll see you again on Wednesday, where we'll keep talking about polymorphism and traits and stuff and dynamic dispatch. It'll be very fun. We'll see you then. Yeah, so bye for now. See you later.